Everybody, welcome back from the lunch break on the second day here of the SU2 conference. We will start the third session with Felipe, Diogo, Moura, Silva from I briefly translate or I try the University of Sao Francisco. And he will talk to us about turbulence models and especially a comparative analysis of BSA and SST model. So, Felipe, the floor is yours. Take it from here.
Okay. Hello, everyone. My name is Felipe Diogo, and I'm currently pursuing a mechanical engineering bachelor at Universidade Federal do Vale do São Francisco. First of all, I would like to extend my gratitude to Dr. Fernando Grossi for all of his support in this work. In the early stages of a conceptual project of an aircraft is one of the most important ones. The knowledge about the flow behavior in different conditions over the airfoil is important for decision making, since it might indicate a more efficient aircraft. So, a high fidelity analysis becomes crucial. Moreover, the evaluation of desired accuracy for the analysis is an imperative part to deliver reliable results. And not least, to balance the computational cost with accuracy is a crucial part in numerical analysis, since it's computationally expensive. The main objective of this work is to compare the influence of two turbulence closure models on flow behavior and its aerodynamic coefficients relative to experimental data. Additionally, a mesh independent study was conducted to minimize the computational cost. For this study, experimental data was acquired from paper that used a variable density wind tunnel to perform tests in different airfoils. These results were documented by Jacobs and Abbott and were available at NASA Technical Reports survey. Thus, with the treated data, it was possible to make this comparison. The domain geometry was configured as O-type domain with a radius of 40 times their virtue. This domain size was reduced based on aerodynamic coefficient variation, reducing it until the value of coefficient started to diverge. The bounds were configured as a far-field boundary condition, minimizing the flow recirculation and pressure influence far from the airfoil, favoring the analysis convergence. Furthermore, the airfoil is a no-slip wall and an isomorphic surface. The free stream conditions are defined to achieve the similarity with test conditions, using the same dimensionless values and turbulence intensity. Furthermore, this analysis was made using the 5G NACA 23012 airfoil and covers a range of 0 to 16 degrees of angle of attack. At this point, tests performed to achieve the best numerical setup, optimizing the parameters, convergence, and speed of analysis. Also, green Gauss was used as a gradient numerical method and CFL number of 0.95 and adaptive, since the implicit time integration allows us to use it to accelerate convergence. The multigrid activated and using the DAP cycle for linear parameters, FGMRES and LUSDS. Further, GST, convective flow, and scalar wind for turbulence, and using Venkatakrishnan as a slope limiter. The mesh was done using Gmesh, and tests were performed to test different types of meshes, aiming to minimize the amount of elements for the final configuration. So, the final configuration was using the unstructured mesh for most of the domain and structured layers around the airfoil that grows in a geometric progression of 1.5 ratio, with the first layer height calculated to assure the I plus near the 1. In the mesh independence analysis, the amount of elements in first layer height were gradually changed, resulting in a small difference in the behavior of flow. In this CPA distribution at 16 degrees, we can observe a small difference from 0 to zero point 0.4 of charge, showing better capture of fine and extra fine mesh of suction region. Further, a greater friction captured at leading edge, mainly due to the refinement near the wall. Once these results have a trivial variation between the fine and extra fine configuration, the posterior results are performance with the fine mesh. For this result, we can observe the transitional SST model, the better capture of transition, beginning with the small fluctuations of velocity and pressure. At this highlighted part, the frictional coefficients in x direction to assume negative values, showing detachment and start of transition to turbulent behavior. These values showing this is what we captured mainly due to the gamma ray data formulation contained on transitional SST model that model the transition for gamma values between 0 and 1, where near 0 is more laminar and 1 more turbulent, become more evident in this region where the frictional coefficients turns negative. The impact on coefficient of critical relative to experimental values for of angle of attack range, but it changed considerably near the star region, where the Spalart-Allmaras house first, increasing the difference from the experimental, while the transitional SST has less divergence at this region. For drag coefficient, it's evident the difference between the curve slope of both models, while the Spalart-Allmaras shows a bigger difference, but not exceeding a difference of 21% relative to experiment. And that range mainly due to the mathematical treatment of fully turbulent flow, while the transitional SST can capture better the frictional and viscous drag due to the nature of complex principle of four equations model. At this point, it's possible to see the Allmaras left curve slope showing a minor difference at initial angles and growing while this grows. At its at all of working range, the transitional SST delivers a good percentage difference for drag and reassure the efficiency for this type of calculation. In summary, this study demonstrates several key findings regarding aerodynamic simulations at two-dimensional airfoil using SU2 and G-mesh. First, SU2 CFD solver proves to be highly efficient and versatile, making us well suited for computing two-dimensional airfoil analysis across the flow condition. The mesh generation process using G-mesh also stands out for complexity and ease, as it can be automated through the scripting in any programming language, streamlining the simulation setup. The Spalart-Allmaras turbulence model provided accurate predictions for lift. Its performance in drag prediction was less reliable for particular case. In contrast, the transitional SST model effectively captured the transitional flow, making more suitable for accurate drag predictions under similar conditions. In terms of computational performance, both turbulence models exhibited comparable time per iteration under the same computational setup. However, the Spalart-Allmaras models were slightly faster, reflecting its advantage in simulation requiring quicker convergence. And lastly, it's evident that well-configured simulation setup is crucial for ensuring the reliability of two-dimensional results, especially at medium to high Reynolds numbers. Overall, the combination of efficient FD tools, robust turbulence models, and carefully designed setup ensures the accurate and reliable aerodynamic predictions. This is the references used in sport. And now I'm open for any questions.
All right. Thanks, Felipe. And yeah, does the audience have questions? And of course, before going maybe to questions, I also want to, of course, thank the co-author Luis Gonzalez on this talk. So I didn't want to drop his name. Wait, Julia?
Yeah, I had a question about boundary condition because I think I read that there is a isobaric boundary condition on the profile or something. You get missed the interpretation.
So Felipe, I'm not sure if you understood the question.
No, I don't understood this. Can you
Okay.
repeat it for me?
Julia asked whether you used an isobaric boundary condition, or if you can maybe talk a little bit more about the boundary condition setup of yours.
Ah, okay. Well, one moment. For the boundary condition in the airfoil, aiming to have no influence in the flow and the results. The setup in the body is the noise slip wall and the isobaric surge. This is mainly due to reduce the pressure influence in the result and in the behavior of flow around the airfoil.
Okay, maybe you repeat your question directly. So that's
So yes, no, the question was like that at some point in one of your slides, I read that you're indeed using an isobaric boundary condition, but I didn't get where you are applying that.
a good idea is to go.
Yes, if you can go back to that slide.
Yeah, I think I can try. So you can say stop maybe, or this maybe.
No, the next. No.
Here.
No, this one, yes.
Yeah.
The airfoil was
Okay.
defined.
Oh, in this isobaric boundary condition in the airfoil is mainly due to reduce the pressure influence in the behavior of flow and in near the stall region, and it's mainly due for this to reduce the pressure influence in the results and the detachment and behavior of flow at all.
Yeah. So I would ask Julio to maybe email the author. So maybe it seems to be a little bit more involved. So Ever, please.
So in the end, you can do comparison between the observed models in SU2 and experiment for results, and between like the Turbulence models, the key errors and error was with respect to the experiment results with neural segments that's about. What were the error bars of the what were the error bars of the experiment for results?
Okay, I'll try to briefly repeat the question, Felipe. So you compared two experimental results, and the question is towards the error bars on these experimental results, because the difference between the transition model and the non-transition model, turbulence model, it has some magnitude, like 10%. And now the question is if maybe the experimental error is also in the maybe even same magnitude. So do you have any information about this experimental error?
No, I don't have any information about the error bars.
Then maybe I have a short question. Because in SU2 we had a time where we had multiple developments in terms of transition models. So the commutations you made here, is that done with a major release version? So is all the code that you used in the main branch, or is it some local development you have there?
Okay, just a moment. No, I don't create the transition, but I just use it for equations. on in the SU2 code. I don't made any modifications at this code.
Okay, thanks. So you use the main version as far as I understood. Are there any further questions for Felipe? If not, let's thank the authors again.